In the cosmic tapestry, forces unseen, a dance of powers, vast and serene, a universe governed by secrets untold. In the grand theater of mysteries unfold, expansion abrupt, a cosmic ballet. In the era of swift celestial display, no center, no end, just infinite sway. A cosmic waltz in the vast astral array. The Hubble whispers its constant refrain, a cosmic heartbeat in an infinite terrain. A discrepancy noted, a scientific quest to fathom the universe. We're put to the test. James Webb peers through the infrared gaze, galaxies distant in the cosmic haze. A new measure, a celestial grace, a dance with the cosmos, an intricate embrace. A dance with the cosmos, an intricate embrace. In the cosmic ballet, the Hubble's ebb and flow. 69, 73, the numbers unfold. In the vast cosmic story, their mysteries told. Scientific minds in dialogue engage, a cosmic riddle on the science stage. The universe expands, a lyrical theme, in the poetic dance of the cosmic dream. Today, let's delve into the forces governing the cosmos, the era of rapid cosmic expansion, and the enigmatic concepts of the universe's center and its limits. Don't forget to subscribe, like, and turn on notifications. Your support fuels the creation of these videos. Hello. There are 4 fundamental forces that dominate the universe: gravity, electromagnetism, the strong force, and the weak force. Each force has distinct characteristics. Gravity, it is the force acting between 2 objects with mass, and it is inversely proportional to the square of the distance between them. The hypothetical particle associated with gravity is called the graviton. Although it has not been discovered yet, gravity plays a crucial role on the largest scales in the universe. Electromagnetism. This force operates between 2 particles with electric charge, and it also follows an inverse square law with distance. Photons mediate the electromagnetic force. Electromagnetism determines the structure of atoms and molecules and governs various phenomena in our surroundings. Strong force. Acting between quarks, the strong force becomes stronger as particles move farther apart. Gluons mediate the strong force, and it is responsible for the composition of protons and neutrons, enabling processes like nuclear fusion and fission. Weak force. This force acts between quarks and leptons and is effective only at short distances. W and Z bosons mediate the weak force, which is responsible for processes such as radioactive decay and the generation of energy in the sun. These 4 forces have different strengths and ranges, allowing them to explain a wide array of phenomena observed in the universe. In the cosmos, the origin of the rotational motion observed among celestial bodies, galaxies, planets, and satellites can be attributed to the following: orbital motion, revolution. Celestial bodies move in elliptical orbits due to the gravitational attraction between them. The cause of orbital motion lies in the swirling and collisions of matter that existed in the early universe. During this phase, matter rotated to conserve angular momentum and, under the influence of gravity, coalesced, leading to the occurrence of orbital motion, spin, rotation. This is the motion where a celestial body rotates around its own axis, similar to orbital motion. The origin of spin can be traced back to the swirling and collisions of matter in the early universe. Matter rotated to conserve angular momentum, and through the influence of gravity, it coalesced, resulting in the initiation of spin. In essence, the source of rotational motion among celestial bodies in the universe can be attributed to the swirling and collisions of matter that existed in the early universe. The assumption that there were no swirling and collisions of matter in the early universe contradicts the laws of physics and is an unrealistic scenario. However, In a hypothetical situation where such conditions are assumed not to exist, the two objects could be attracted by gravity and have the potential to collide. The likelihood of collision depends on factors such as the masses of the two objects, the distance between them, initial velocities, and initial directions. For instance, if the two objects are sufficiently distant or moving in a direction that traces a circular orbit at a high velocity, they may not collide and continue to revolve. The swirling and collisions of matter in the early universe can be explained by the Big Bang theory. According to this theory, the universe originated from an extremely small and dense state with very high temperature, approximately 13.787 plus 0.020 billion years ago. Subsequently, it began to expand and cool continuously. After the Big Bang, the early universe was in a state where energy and matter were evenly distributed. However, as the universe expanded, slight density variations emerged. These variations, under the influence of gravity and other forces, triggered the swirling and collisions of matter. In this process, matter rotated to conserve angular momentum and, influenced by gravity, coalesced. The atoms and particles formed in this way eventually gave rise to the creation of stars and galaxies. Scientific theories describing the early history of the universe are based on the Big Bang theory, general relativity, particle physics, and other frameworks. These theories make predictions about the temperature, density, expansion rate, types and quantities of matter, cosmic background radiation, and more. Scientists can validate these predictions by comparing them with observational results, providing a comprehensive understanding of the early universe. After the Big Bang, the early universe existed in a state of extremely high temperature and density. At this point, it is believed that the universe was governed by a unified force encompassing the four fundamental forces: gravity, electromagnetism, strong force, and weak force. However, as the universe expanded and cooled, the four forces gradually separated. During this process, the universe underwent a period of rapid expansion known as the inflationary epoch. At the end of the inflationary epoch, the universe remained extremely hot. Energy and matter were evenly distributed, and there was the possibility of mutual transformation between energy and matter. During this time, the universe was dominated by radiation energy, with the density of radiation much higher than that of matter. At this stage, atoms did not yet exist, and fundamental particles such as quarks, gluons, electrons, positrons, and neutrinos were present. As the universe continued to expand and cool, quarks and gluons, under the influence of the strong force, formed the building blocks of protons and neutrons, known as hadrons. The universe was then dominated by hadron energy, and the density of hadron energy was similar to that of radiation energy. During this period, matter and antimatter coexisted in equal amounts, undergoing collisions and transforming into energy. Further cooling of the universe led to the breaking of this symmetry between matter and antimatter. This was due to the different rates of creation and annihilation between the two. At this point, the universe was dominated by lepton energy, with the density of lepton energy higher than that of hadron energy. Electrons, positrons, neutrinos, and other leptons were present during this phase. Continued cooling resulted in the annihilation of electrons and positrons, converting into radiation energy. The universe was once again dominated by radiation energy, with the density of radiation energy higher than that of lepton energy. During this time, Neutrinos, protons, neutrons, electrons, and other particles were present in the universe. Approximately 3.8 billion years later, the temperature had decreased enough for protons and electrons to combine, forming hydrogen atoms in a process known as recombination. At this point, the universe was dominated by matter energy, with the density of matter energy higher than that of radiation energy. The universe contained hydrogen atoms, helium atoms, neutrinos, and other particles. Following recombination, the universe became transparent. The radiation energy first emitted during this period remains as the cosmic microwave background radiation observable today. At this time, the universe had slight density variations, leading to the swirling and collisions of matter under the influence of gravity and other forces. Matter coalesced, forming atoms and particles that eventually gave rise to stars and galaxies. This detailed explanation of the early history of the universe is based on the contributions of numerous scientists and researchers. This detailed explanation of the early history of the universe is based on the contributions of numerous scientists and researchers. The Big Bang Theory was initially proposed by Belgian priest and physicist Georges Lemaitre in 1927. General relativity was completed by German physicist Albert Einstein in 1915. The standard model of particle physics was developed by numerous physicists from the late 20th century to the early 21st century. These theories play a crucial role in explaining the early history of the universe. Let me provide you with a detailed explanation of gravity, the force that governs the universe. Gravity is a force that acts between all objects with mass, proportional to the product of their masses, and inversely proportional to the square of the distance between them. While the hypothetical particle associated with gravity is believed to be the graviton, it has not been discovered yet. Gravity plays a crucial role on the grandest scales in the universe. Throughout the evolutionary process of the universe, gravity has been instrumental in bringing widely dispersed matter together, forming stars and planets. This gravitational cohesion allowed other forces such as the strong and electromagnetic forces to manifest in the material world. The formation of structures like stars and galaxies is a consequence of the two essential conditions for the emergence of complex systems: the density of matter and the flow of energy. Gravity also exerts its influence on time and space. According to the theory of general relativity, gravity bends space and slows down time. In regions with strong gravity, time passes more slowly and light is bent. These phenomena can be observed through gravitational lensing effects or the detection of gravitational waves. Moreover, gravity gives rise to intriguing phenomena such as black holes. Black holes are regions where gravity is so intense that even light cannot escape. The interior of a black hole remains unexplored, posing the challenge of the information paradox. Understanding black holes necessitates new physics, including theories such as string theory or loop quantum gravity. Let me provide you with a detailed explanation of electromagnetism. Electromagnetism is the force that acts between two charged particles and is inversely proportional to the square of the distance between them. The mediator particle associated with electromagnetism is the photon. Electromagnetic force plays a crucial role in determining the structure of atoms and molecules and various phenomena in our surroundings. Electromagnetism unifies electric and magnetic forces into a single force. The electric force repels like charges and attracts opposite charges. The magnetic force acts between objects with magnetic polarity, repelling like poles and attracting opposite poles. Moving charges generate a magnetic field, and a magnetic field can induce the movement of charges. For example, a current flowing through a wire produces a magnetic field, and bringing a magnet close to the wire can induce current flow. This phenomenon is known as electromagnetic induction. Electromagnetism can also transmit energy in the form of electromagnetic waves. Electromagnetic waves are generated when electric and magnetic fields oscillate perpendicular to each other. Examples of electromagnetic waves include visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. I will explain the strong force in detail. The strong force is the force that acts between quarks, becoming stronger as the distance increases. The mediating particles of the strong force are gluons. The strong force is responsible for forming protons and neutrons and enables nuclear fusion and fission. The strong force can be explained by the theory of quantum chromodynamics, QCD. QCD describes how quarks and gluons interact through the strong force. In QCD, quarks and gluons possess a property called color, which is categorized into red, blue, green, and their corresponding anti-colors. Quarks and gluons exchange colors as they transmit the strong force, and they can only exist in a color-neutral state. This is known as color confinement. The strong force is very weak at short distances, but becomes extremely strong as the distance increases. This characteristic is called a non-dissipative force. The non-dissipative force refers to the phenomenon where new quarks and gluons are generated during the process of transmitting the strong force by quarks and gluons. Because of this, quarks cannot exist individually and always combine with other quarks to form hadrons. This is known as quark confinement. The weak force, also known as the weak interaction in Korean, is the force that acts between quarks within an atomic nucleus and becomes weaker as the distance increases. The mediating particles of the weak force are the W boson and the Z boson. The weak force enables the stability of atomic nuclei and radioactive decay. The weak force, along with quantum chromodynamics, QCD, is a component of the Standard Model, which is part of quantum field theory, QFT. QFT is a theory that integratively explains matter, energy, space, and time. The Standard Model is the most successful theory in physics for classifying and predicting the fundamental particles and forces of the universe. Like the strong force, the weak force acts between quarks that possess color charge. However, unlike the strong force, it also acts on electrons and neutrinos, which carry electric charge but not color charge. The weak force is transmitted through the exchange of bosons, which are particles that interact weakly between quarks and leptons. Bosons are similar to photons, the mediators of the electromagnetic force, but they have mass and can be charged or neutral. The weak force is weaker than the strong force at short distances, but becomes stronger than the strong force as the distance increases. This characteristic is called a dissipative force. The dissipative force refers to the phenomenon where new quarks and bosons are generated during the process of transmitting the strong force by quarks and bosons. Because of this, quarks can exist individually and cause radioactive phenomena, such as nuclear fission or fusion. This concludes the detailed explanation of the weak force. Let me provide detailed explanations for both quantum chromodynamics, QCD, and quantum field theory, QFT. Quantum chromodynamics, QCD, is a theory that describes how quarks and gluons interact through the strong force. Quarks and gluons possess a property called color, and they can only exist in a color-neutral state. Quarks always combine with other quarks to form hadrons, while gluons mediate the strong force between quarks and other gluons. Quantum field theory, QFT, is a quantum theory that describes fields. A field is a physical quantity distributed across space and time. For example, the electromagnetic field is created by charged particles. QFT quantizes fields so that the values of the fields are expressed as operators. This allows the interactions between fields and particles to be explained. Both QCD and QFT are components of the Standard Model. The Standard Model is the most successful theory in physics for classifying and predicting the fundamental particles and forces of the universe. It explains 3 of the 4 fundamental forces: strong force, electromagnetic force, and weak force, using QFT, while the strong force is specifically explained by QCD. The question of where the center of the universe was when the Big Bang occurred is based on a misconception. The Big Bang was not an explosion at a specific point in space. Rather, it was the rapid expansion of the entire universe from an infinitely small and hot state. Therefore, the concept of a center of the Big Bang does not exist. The Big Bang happened simultaneously everywhere in the universe, and the universe continues to expand. The Big Bang theory explains the evolution of the universe from its inception to the present. However, questions about what existed before the birth of the universe and why the Big Bang occurred remain uncertain. Answering these questions requires new theories in physics. Similarly, the question of where the edge of the universe is also based on a misconception. The universe did not start from a single point, but rapidly expanded from an infinitesimally small and hot state. Therefore, there is no center or edge of the universe as we commonly perceive it. The universe is expanding simultaneously in all directions, and the limits of the observable universe are related to the structure of space-time. The boundary of the observable universe is determined by the maximum distance that light, traveling at the speed of light, could have traveled from the beginning of the universe until now, which is approximately 93 billion light-years. However, it is difficult to say that this is the actual end of the universe. There may be regions where the expansion of the universe is faster than the speed of light, known as the unobservable universe. Furthermore, it is still uncertain whether the universe has an actual end or if it continues to expand infinitely with no end. Answering these questions will require new theories in physics. There is a claim that the scientific community was stirred by the recent interpretation that the expansion of the universe observed by the James Webb Space Telescope may not be as fast as previously thought. The rate of the universe's expansion is quantified by the Hubble constant, which describes the relationship between the distance and velocity of objects in the universe. The farther the distance, the faster the velocity, according to this constant. Multiple methods exist for measuring the Hubble constant, such as using specific celestial objects with standard luminosities, standard candles, or utilizing the remnant radiation from the early moments of the Big Bang. However, these methods yield different values, creating a discrepancy. The use of standard candles suggests a Hubble constant of approximately 73 km/s/MPC, while methods involving the remnant radiation estimate around 67 km/s/MPC. This difference is statistically significant and has substantial implications for our understanding of the theory behind the expansion of the universe. In response to this issue, the James Webb Space Telescope proposed a new measurement method. Since it can observe the universe in the infrared spectrum, it can capture images of galaxies located even farther away. Through this approach, The Hubble constant was measured to be around 69 kilometers MPC. This value falls between the previous two methods, providing a statistically compatible result. These findings reduce the likelihood of errors in the methods used to estimate the universe's expansion rate. They also suggest the need for a reevaluation of the theory regarding the expansion of the universe. The scientific community is currently discussing the accuracy and reliability of the James Webb Space Telescope's measurement methods, and whether a new model for the expansion of the universe is necessary. This is to explain why the scientific community is agitated by the interpretation that the expansion of the universe may not be as fast as what was recently observed with the James Webb Telescope. Thank you for watching for a long time.